Okay, welcome everyone to this new webinar of the series organized by the IFAC Technical Committee 9.4 on Control Education, together with the IEEE Control System Society Technical Committee on Control Education. And today I have the pleasure to introduce you Claudia Fernanda Yasar. She is from the Department of Control and Automation Engineering at Yildiz Technical University in Turkey. She earned her PhD in mechatronics from Castilla-La Mancha University in Spain, where she received the Best Spanish PhD Thesis Award in robotics in 2017. She had academic positions in Colombia, Spain, and Turkey now, and she's very fond of control education. And today she will talk about bridging theory and application in intelligent control education. Claudia, thank you very much for being here. The stage is yours.
Thank you, Antonio. Thank you, everyone. To you all for being here. I'm very happy to share my work with you. So thank you for the presentation. My name is Claudia Fernanda Yasar. I am an associate professor at Yildiz Technical University at the Control and Automation Engineering Department. I am going to speak about bridging theory and application in intelligent control education. This is particular a project I have been working on for some years, 2.5 years. And I am going to show you many examples and experimental work also that I do in control education, and most of them in intelligent control. So here we go. My goal today is going to be, I want to share how I integrate control concepts through hands-on and digital learning experiences. So we all know that control theory is abstract, that many of our students struggle to connect what is the equation, mathematics, physics, chemistry, whatever the plant is, theoretically and the practical application of the system. We all are working, many of us are studying or working in universities. We know that labs are limited and they are very expensive. I work in Turkey, where we have a lot of students, and it's very difficult to give to everyone a lab platform. We need to bring simulation and experimentation closer to learning. That's what I have been learning these years that I am working in this area. The idea of mine is trying to motivate, trying to enhance engineering-oriented analysis, problem solving, and self-learning skills in our students. So try to give them some practical skills to apply theoretical knowledge, motivate critical thinking, analyze, evaluate control performance, solve complex problems in their own, give some data-driven expertise, get some data for them to work with, and try new methods, new technologies, not only for new controllers like data-driven controllers now or hybrid control, but also I'm trying to use new tools for teaching. So trying to see what is available and how can integrate it to my curriculum. Real-time experiments I am also trying to do with my students. So it gives the hands-on learning. And many of my experiments are low-cost platforms. I have to tell you that in this university for 7.5 years, I have been teaching measurements and sensors for control engineers, the students of the second year, mechatronics in the third year, process control and real-time control for the fourth year. At the master level, I am teaching system dynamics, modeling, and simulation. Also, the project of mine in intelligent control systems. In every single course of mine, the student have to give a homework or a project. It can be a simulation or a real experiment. Intelligent control systems. So we all know that it's coming from conventional, the basis is conventional classical control, but it is used to deal with complex processes that the traditional methods cannot control, or we are looking for an efficient option. It has learning, adaptive, and organizing functions. I am bringing here two examples from my lab. So most of the things I'm going to show here are from my lab. This fixed wings aircraft, this is my lab, has been done by my students. And we are flying this aircraft all over the campus. But it is working pretty well. But when there is a strong winds, like these days here in Istanbul, it works, the controller works different. So there are a lot of disturbances, environmental disturbances. And also we have heated, and even the dynamics of the system changes if there is any problem, you know, in the plane itself. So we need at least a controller that can adapt and allow us landing safely. On the right, I have an example of a project of mine in climbing robotics. So there are some robots that are climbing vertical walls, and they are having some sensors, and they are doing inspection in here, for example, in metallic walls, looking for corrosion, trying to check with cameras how the material is, if we can predict if there is any crack, etc., etc. The problem in here is at the motor side, it has two wheels. For example, this one, this is a differential robot. It has two motors, each motor attached to the wheel. We have magnetic magnets, to attach to the metallic wall. And we have also some like vacuum caps for friction to reduce slippery. And a lot of forces are going to be affecting at the motor side. Friction, column friction forces that are non-linear, magnetic forces, strong magnetic forces that attach the system to the wall, gravity forces that sometimes helps the movement or against the movement. And also, because this has to move around, there are going to be some changes in position. We say changes in the head angle, and the inertia is going to change. So there's a lot of internal disturbances. This is how our plane works when there is wind, starting some bounce there. And this is how another climbing robot of ours works. Here we have magnetic tracks. Also, it's a differential robot. It has two motors, and it has to go to a specific coordinate. This one here, if you see, we were trying to put IoT in there. So, intelligent control systems. I have been working in a project developing curriculum, and the first lesson of mine in my lesson in intelligent control is working with computational thinking tools. Here I give to my students some general information about control principles, tools and techniques. Try to make the classroom more homogeneous, because they are master students. They are coming from different disciplines, different engineering. Some people are coming from abroad. Some people are coming from different universities here in Turkey. So I don't know how much, they really know how much they had practiced, simulated, or do experiments. So I give a lot of examples, tools, different sources for them to learn. This is the first week. There is another part of my course that it concentrates in dynamical systems modeling, dynamics and modeling, plus simulation. So we have, specifically here, we are working most of the course with something that I call DC lab. What is the DC lab? It's just a DC motor with an encoder, incremental encoder, a reduction box. How many things we can do with this thing in your classroom? I mean, it's unlimited. We packed and we put some hardware that is going to be also cheap hardware for our students, and then everybody can have a set. I also use the TC lab I bought it from Amazon. This is not mine. You can have information from AP Monitor. You can buy it, and there are many resources. So I am using this device also to try some experiments for intelligent control. First, I need model, I need dynamics, because in many cases, I go for hybrid controllers, model-based plus an adaptation law, or model, and also we have data-driven, and then we mix them. Important, have a look at the 5th week. We can also work with data that is online. And I have here coastline prediction using climate change models. And I go work with regression models. And I can do predictive modeling based on climate change. There is already a lot of information about variables, environmental variables that have to do with the sea. And there are some web pages already that they give us, they project us in the future until 2050, how the sea level is going to change around the world. So I am using that to do prediction and comparing with the data that is on internet. Then after this module, I go to data-driven modeling. Semi-empirical model estimation regression with the TC lab. That TC lab is 2 heaters with 2 sensors. And we can work it like multi-input, 2 inputs, 2 outputs, and we can work with heat exchange, like disturbances. We can do many experiments. So I do regression and classification, and I give the data, and they can run their models, test the models, which one is better. In the 8th week, I use a webcam, image processing, and I do object classification using deep learning. In week 9, I use Python and I use MATLAB together, a very good example of interoperability. So we get the advantages of Python, Google Colab in the ecosystem, and we bring it, to MATLAB to work with visualization and some other things. Historical data from internet. Finally, 10 model-driven and data-driven control. I have my motor. I do with the DC lab, model predictive control. I work in model reference adaptive control in simulations, but also I will show you that now I have also the experiments with model reference adaptive, extreme seeking, simulation, and DC motor position with facet. This is still a simulation. We are going to apply soon, the experiment as well. So these are 13 live scripts, 13 subjects that are shared online. If you want to go and have a look, here I have the code. And you can benefit, you can download each week separately, and it's coming with a lot of data. Educational challenge and my strategy. So I'm sharing every week 1 or 2 live scripts, and with a lot of information, programs, and definitely I have to be in the classroom at least 3 hours every week, teaching them, running the program with them. And it's throughout 3-hour sessions, covering intelligent control, concepts, control theory, giving examples, using the computational tools. Very important, control performance evaluation. And comparing, a clever controller, intelligent control with classical, so we can see if it's really, really better, and under which criteria. I'm sharing that interactive live script with extra activities like lab exercises, and the live script are application-focused materials. It also has videos, simulations, experimental data to work with, and real-time experiments. You can plug even the device, and I have the software there to start working with it. Computational thinking tools, there are many. I will show you a very important one here, the live editor. Interactive programming and documentation. So the idea of having a project, because I give projects to my students and they have to give it in the final, the last weeks, and they have to present it, but they have to write as well. So the idea is they have to prepare their own documents as a live script. I also give them, and the programs are in there, step by step. We can run them, everything pops up, the results. So they learn to work in this way. It creates an interactive narrative, like a report, like a book. And you can publish the reports. You can ask your students to give it as a PDF, as a Word document, and you can also use LaTeX in it. This is an example of a live script. Titles, subtitles, you can paste pictures. For example, you can link it to a web page that is showing you stories about that particular subject that you are working in. Then you can start with your models. This is a mass damper spring system. You can go to the tutorial and learn more about how to model these things, like the controllers, etc. I have the models, state space model, and a transfer function. I can have a look, for example, if I change the parameters mass or the viscous friction coefficient or the spring constant, what is the pole location of that transfer function? Or I can check, for example, the response to a step. So that's the way I'm asking my students to work, to program, and to explain everything. These lab scripts, many of them are coming with videos. I gave data in the lab script, at least they can see how the experiment is performed. So I have to create this. There are not many things, but these are the things I have for the live script. Or I am running an image processing and classification algorithm, and I show how it works in a real robot. So there are many things here, but they have to do with the live script. If you are interested in the channel, have a look. Here is the QR code. Important for me, starting with measurements and sensors and how to work with them for control. So the basics, we have to speak about the basics and be a little bit, be picky about, measurement. So it says one can control only what is measured. Without a good measurement, you can not do a very precise controller. So I will show you some examples of application with my students. Integration of accelerometer and GPS data for motion analysis using mobile devices. The advantage of having all mobile phones. Our students, many of them, have accelerometer. We also have accelerometer, magnetometer, and GPS. What can we do with it? We can download a program. We can record like our steps, and then the students can get that data and do some analysis. Count the steps they did and check which of these peaks or maximums might be a step. Report the number of steps. Oh, you have a GPS. You can download the program, show on a map where you have been. And even with the GPS and this information, you can report speed as well. Have a look, the dark blue ones, it is speed in kilometers per hour. So these were very slow, and the red parts and orange parts is where they were running. So this is one of the ways to work with my students. Another example, I have multiple examples. A very good one I like very much is this one. What is very typical, you work with Arduino Uno. You have here, we have developed a new, at least a lab-made optical sensor with a diode and a receiver, an emitter, and we make here an array. And with the reflection of light, we can check the force. And then we can calibrate it. If we have a very well calibrated load cell, we can check and make it close, and use them. If it is calibrated, the optical sensor you can use for gripping, for haptics, to give to the system the sense of touch. You can make it clever in many ways by using touch. How I look, this is an STM card. This is very basic. It was the beginning, just to see. There are some diodes inside receivers, and you can see how it changes. So now the idea is how to use this experiment to measure force. Then we were working in different sensors. We were molding them, and we were applying force to each of the sensors. On the other side, at the opposite side, we have millivolts. Then we were applying a step, which means some grams here in the x-axis in this graph. We are increasing, and at the output side, we have millivolts. So step by step, we were changing, going up, increasing grams, and then we are going down. And if we repeat it, we obtain this kind of hysteresis graphs. Then I said to my student, let's calculate hysteresis by gram. And we come up with this calibration table where we can report per each gram what is the error in hysteresis. It was kind of linear. We could see from the very beginning, but then when we increase step by step, we could see the hysteresis. Then we say we need to work with, I wish it were linear, fully linear. Let's have a look and report non-linearity. And it is given in percentage. And in the same way, we step by step, we increase it. Here we have the hysteresis, and we name this line, this red line, terminal-based straight line. Endpoint straight line is called. So it's a calibration curve. It can be used, to make the system clever with some haptics. Now, I'm going to explain some examples in dynamical system modeling and control. I speak to my students about how important is understand all about the process inside and outside, and define your control objectives in a logical way. Remember that there is a dynamic component. What does it mean? At least try to obtain a reduced model, the dynamics inside in the system. And be aware that there are some constraints, limitations, and be aware which assumptions you make for that specific model before doing control. That is important. Right now, I have a work in intelligent control, the DC motor dynamics modeling and position control. So we have the motor with an incremental encoder with the reduction box. We put Arduino Uno, and we are learning some theory dynamics and some classical controllers. Then we can simulate them. Then we can try with the little lab, the DC lab. Does it match? So the simulation has to follow the real experiment. If it doesn't match, it's because your simulation is too ideal. You have to make it realistic. So add friction, add saturation, be aware what else is affecting the system, but it has to be similar. Then we build some understanding of everything that is happening there in that experiment, in size and intuition for real world challenges. Then we can come to the theory. If this one doesn't work, we have to start, running in this side. This is an experiment with this DC lab. Normally, I work with a reduced DC motor modeling, only the mechanics. And here I have the torques coming from friction that are nonlinear. I say to my students, if we come up with a controller that can compensate for this friction, so we have a linear model, and we can use Laplace, and then we have, if we say we are going to control position, so theta divided by the input, that is voltage, then we have a reduced model, second order system. We are going to control position. Finally, we have parameters K, J, V, motor constant, motor inertia, viscous friction coefficient. We can group them. We have a model, and we have to identify only two parameters, A and B. We can use a parameter identification toolbox that is going to work and tell us these values, A and B. Let's have a look how I am doing. This is my live script that I'm sharing with my students. Some information about how it works, table of contents. I'm explaining what is in there, defining variables and parameters, models, the transfer function, state space representation. If you have the device, I mean, if you have a DC motor with an Arduino and you can plug it, I am giving the software. You get the data, you save the data. Or if you don't have the experimental platform, I am giving the data. You click a video, you see how I got this data. Have a look. The input to the system is in red and the output is in blue. This is coming from a position controller, a P controller, a very basic controller that I do in position, some steps that are going to change, and then I go feedback, P control, this is the motor, and I obtain the output. So have a look that the input in red and the output in blue is kind of similar. It's not exactly because it's just P control. It's not enough, but at least it's going to allow me to do a good parameter identification in closed loop. I am going to share this thing. Where was it? Here is how I work with the parameter estimation toolbox. I upload the data that I share with my students. Then there are some optimization functions. The toolbox is trying to follow the experimental data that I give, and it's going to tell me what is the value of A and what is the value of B, the best value to match this graph. Experimental cost going down because it's iterating, and A and B are changing. How I looked at A, that is the blue, was the initial value was very far. So it's approaching. After some iterations, we are going to have A and B. To accelerate this. It says estimation converge, and we have the values A and B reported here. A 206 and B 20.4. So now we have the model, a reduced model, and we have some parameters. Now we are ready to do some control. These are lab hardware low-cost platforms, Arduino and H-Bridge. This is the motor driver. Motor with encoder and reduction, and we pack everything. We put an indicator. What do we need as a software? We need to generate PWM, set the input in voltage, the duty cycle. And we need to read the encoder. But because it's a motor, we need to go back, forward and backwards. And then we are going to have here a function. And if we can generate PWM and read the encoder, we can close the loop. This is the motor, the encoder. We can do open loop, closed loop, and test with our students many controllers. Real-time control projects. So coming from theory, going to practical experimentation. I'm trying to work first, at least in model-based design, and I am sharing materials, live script materials. I can also go to rapid prototyping and use the real-time system. The students are going to have, experience on hands-on practice, and I'm going to guide them with live scripts. It's going to be a practical control education that is I'm trying to enhance some skills in my students. We have the DC lab. We have the plant simulated here. That is the second order transfer function with A and B as parameters. I model the friction with them. I have a model here. It's not linear, it's complicated. It's very difficult to model friction. At least one of the models, we can get it theoretical and put it there. And saturation, what are the maximum values that the control signal can get? You already have A and B. Then I say, for example, do a PI controller. Here we have the response to one step. The green one is simulated. The real system response is in blue. Are they similar? Yes, they are. They have similar things. They have the settle time here. The overshoot is kind of similar. There are some differences. The real one is the blue and is coming with some chattering. There is some static error. Of course, this encoder gives a count every 30 degrees. The resolution is very low. Anyway, we can make it better with better acquisition system. And here I have Arduino Uno and a better encoder. But anyway, it is pretty similar. Another important thing is, analyze how the system responds to inputs and check for at least the static friction. And we can generate a 1D table, very easy. We have the motor. We have to increase from 0 and give PWM. Here I have forward is going to turn and until 100% PWM or negative, close otherwise. And we are going to we can record for each command what was the speed. We get it with encoder. Increase PWM. Have a look at the speed. There is a part here that it doesn't move. This is the static friction. Keep it in mind because you should know that there is a non-linearity there, so don't ask the controller to work in that area. As well as you have identified what is the saturation, the maximum speed. Don't tell the controller to work in these maximum speeds because there are no linearities in here. So try to work. Here there is a large non-linearity, but we can use anyway this part, like for example, a speed controller, an open loop. If you know that given this command, you are going to have this speed, you can use this data, save this data, and tell, do you want this speed? So go and give this PWM command. As my students are doing, open loop. Now we are going to do speed control following a sinusoidal. And this is open loop, just using that 1D table. So we have the encoder, and here we have the 1D table. Or closed loop, then you get the encoder, get the feedback, put at least a P gain and check. So you are going to have a nested inner loop and then a closed loop. This is input-output response, but I am asking for error signals and control signal. I need to be sure that you are not saturating the controllers. We can work in position control, following a sinusoidal, or here on the right, I say to my students, we are working with motor and we are working in position. I need critical damped responses. The fastest you get the settling time, and I need almost 0 at the steady state. I don't want overshoots because it increases, it generates a behavior that is not good for robotics. It gives problems, it gives vibrations. Then I will look for critical damped responses. Simulation and student projects. So it was 2 years ago, we modeled this motorbike. There are some similar, on internet, you can get from internet these models. And the idea is, for this motorbike, we need to do cruise control, speed control here for the rear wheel, and also control the balance. So you can have the system and closed loop closed loop speed controller, and check how the system is going to perform in simulation. This is SimEscape, the motorbike, the mechanics. I'm closing the loops, realistic loops with motors, with friction. If you click here, you go to saturation. Have a look at our motor here, our model. The blue one is without control. I will come back here. And the green one is when the motorbike is balanced. And this is the speed controller, rear wheel speed controller. So you can run the simulation. Once you have that, you can tell to your students to try to experiment with a realistic platform. It was done in the course of real-time control. Here I am balancing the motorbike just with mechanics. There is no control. There is just the gyroscopic effect. The motor is full power, full PWM, and it generates, it allows me to balance the motorbike mechanically. Or you are a control engineer, so put a sensor and closed loop, do a closed loop controller in position. Keep it steady. Also, here we have a speed control. Testing a speed control. This motorbike can go reverse as well. Forward and reverse. It's the first motorbike that I see that goes in that way. What can we do with motors, controlling DC motors? Many things. This is an example of process control. We are controlling the liquid sloshing in water tanks. This is a problem of transporting liquids. The one uncontrolled, it has only control of the DC motor in here. And now the one that is coming with an open loop controller. I can get the dynamics of the sloshing effect and invert the dynamics, and I get, a reduction in that sloshing effect. We go and work also with build DC motors, speed control. This is Texas Instruments, cars and drivers. We also can go build DC motors with controlling. These are force control and inertia control. Switch off this. Okay. So we are moving one, and it is feeling it and reproducing the same movement in here. I say to my students to do it, checking the control signal. What else we can do with motors? Have a look at this experiment of ours. With my student, I said, we can do like a kind of glass for people who have tremors, like people with Parkinson, or we also can have tremors later on. Then being able to drink water while the hand is shaking, so endpoint control. We check on internet and we found the spoon, and it was patented. So I say, we didn't see the glass. So we tried to patent this work in Turkey, and it was patented. And also we tried international, and we passed the technical report. And in Turkey, we got a medal, one of the best patented, the silver medal we got with this glass. What do we need? Controlling two motors, and there are some accelerometers in here. Model-driven and data-driven control, image processing with a webcam, classification. The robot is classifying orange and apples. I know that there are many programs already on internet that for these two fruits, but we have to optimize our. Why? Because of the computational cost, because of the light in our lab. And I told my students to learn from the ones on internet and adapt it for our application. This application was done in MATLAB. All the deep learning algorithms for classification done in MATLAB. The robot was built In my lab, all the mechanics were printed there. Even the gearboxes, helicoidal gearboxes, were developed there. Is this a control with the step motors? But at least because they are cheap, and then we put an encoder, and like that, we come up with this project. We also can do many things with historical data that is already available on internet. This is a very nice example of unsupervised learning using MATLAB and Python together. So we go to data generation and preparation, the most important part for this, for prediction, for doing prediction using RNN LSTM models. We do prediction and forecasting. The data is coming from the temperature of a city in the USA, in Seattle. And we build, after preparing the data, we build the model. We did some tests, and we optimize the hyperparameters. We did the training, testing, validation. We do prediction, and then we do forecasting. Here we can see from May to November 2015, data, actual data in blue, prediction data in red, so it is following, forecasting the future in green with the model, and the actual values of forecasting here in black. So this is how it works. We have a live script that works with teaching you how to install everything in Python to work with MATLAB, all the libraries, importing the data, doing some tests, Gaussian distribution, kurtosis, probability plots. We go to time series. We are working with time series, so correlation, autocorrelation, training, testing, validation. We use recurrent neural networks, forecasting, and we have some plots. Here is going to show step by step how to install and where to get from all the libraries we need. Environment, Google Colab, Python, TensorFlow, and Keras, all working together, and everything called from MATLAB. The libraries that we use. Data importing. The data comes from internet. We have to check for holes. We have get the data and check if it's Gaussian, because we have to check that. And probability plot. This blue line has to be very close to that black line. This is the time series, January 2012 to January 2016, 4 years data. We check rolling mean, rolling standard for seeing some trends to optimize our models. Autocorrelation, to do prediction, this data should be very close to 1. Then we do the training. So this is more or less what we do in live scripts. Prediction plot, pretty similar. And then forecasting, some days ahead in 2015 in November. Model-driven and data-driven control. We come to this subject. We are doing with a DC motor, with the DC lab. We already have the plan. Try some MPC controllers. Even we did with the toolbox, ready toolbox. And then optimize it. You can simulate it and you can do it real time. Have a look at the results. Response to added step input. We have the reference in red, the real time in blue, and the simulation in yellow. Remember that you have to plot the control signal. So I try to increase the speed just before getting the overshoot in both controllers, but never pass 100%. That was the duty cycle, the PWM signal that is allowed. So I put it to the limit and see how fast the system can get and check simulation and real time. simulation in yellow, real time in blue. We can also do with classical control. So here I have the MPC and the PI controller. And I say to my students, let's get the same settling time and try to work, with the maximum control signal that you can give. And then we have the PI in yellow, in green, and the MPC in blue. The same settling time. There is an overshoot because it's a PI controller. And how I looked at, we check for the PI controller and we check the control signal. I cannot go faster because I reach already the saturation. Here we have for the MPC, the signal. Here I reach saturation, but here is still I can go even faster. The MPC can go even faster. And it gives me a better static error. The green one was having chattering, but the blue one, there is an error in there. Maybe you cannot see it, but there is the red line and the blue line is at the top. Anyway, model reference adaptive. We design a checking table. What do we need? 2 motors, control 2 motors, and following an earthquake signal. Model reference adaptive plus PID control. 2 degrees of freedom. Parameters of the PID, parameters of the model reference adaptive. I said plot input-output response. Always plot the error. Always plot the control signal and make your comparisons or evaluate the performance. We have also, in the last session, we have model-driven data-driven control with fuzzy logic control for a DC motor. This is still a simulation. Very intuitive, to learn how it goes and how to work the membership function plots. This response, I know that can be better. I prefer going to the experiment and coming back to the simulation and see how it works. Research and intelligent control. Designing climbing robots, we have been working in our department with our students. After taking this course, I have some of them in my lab. The robot that I show you with the differential driving is here. We use a disk space for that. For the one with tracks, magnetic tracks, we have, this is a very good one, climbing robot programming diagram. The master is going to be a Raspberry Pi. We are running everything with Node-RED as a main program that manages motor drivers, path following, orientation. We can use the camera for inspection, joysticks for manual operation. All the data that we have with the camera and with the corrosion inspection can be the position of the robot. All of that data can be in a web browser, and we have some sensors that we need, ultrasonic sensors and a capacitor sensor that is missing here. Sensor fusion, IoT, and deep learning for inspection. That's how it works. The one with magnetic tracks and differential robot. We're going to go up. Oh, pardon. Why it went that far? We're just trying to. It's going to go to a specific coordinate. Start the camera. And then we can start with some deep learning algorithms for inspection. We have some other, still developing this one. It's with BLDC motors, Texas Instrument cards. We are moving it in the metallic wall, but it's still a lot to do in control. But this one already has, the algorithm to detect some corrosion, at least some colors, some indication that there might be a problem in there. This one, build DC motors, and we have these magnetic wheels. Results and personal achievements. Many of these things are published. My students are doing their projects, and I am also publishing the live scripts and the simulations. And I mean, you can find it on internet. In these 2.5 years, we have published 3 papers, SCI papers, Q1 papers. One is optimized deep learning approach for forecasting day-ahead electricity prices. Remember that I showed you the LSTM. That way with temperature. We learned there, and we try with day-ahead electricity prices. We published in electric power system research. Then with the climbing robot with the magnetic tracks, we published the controller, corrosion inspection, IoT integration, deep learning, and advanced control, multimedia tools and applications. And the last one was this adaptive speed control of climbing robots using modified model reference adaptive controller, IEEE transactions on industrial applications. This one is 2025. International conference, many. Very important one, this IEEE conference. And we were selected as because it was a good paper, and we published this 3rd journal in there. So we make it better. We did a lot of experiments, and we published that journal. Then I went to Budapest for the IFAC symposium on advances in control education, and I present data model predictive controller. We also have some, our own Turkish conference. It is called the Talk. Very active community. We are publishing everything in Turkish. I have even more. This year I didn't put my things here, but they are also in intelligent control. Conclusions and highlights. Bridging or come together, theory and application together for teaching control and for teaching intelligent control. We believe that we have a novel curriculum because it combines model-based, data-driven methods for model intelligent control systems. We use cutting-edge topics. We are working with AI, with deep learning, and we are also doing predictive modeling. Hands-on learning. We try to encourage in the students project-based education, and they have to write, and they have to come with the experiment, and have to explain. And we are using low-cost hardware. Innovative education. We merge AI, intelligent control, and we are using many advanced digital tools. Accessible learning. We promote open and affordable educational environments with low-cost hardware and a lot of shared materials. That full curriculum in intelligent control is now on internet in file exchange. Skill development, strength, analytical thinking, problem solving, and independent learning in our students. Automation and interoperability. There is a smooth integration between simulation, experimentation, and even we have interoperability between programs with Python and MATLAB. Positive impact, I would say in this year, a lot, because we have had very good student feedback. We have had publications that are important for the students, for their masters, for their PhDs, and successful project outcomes. So this is coming to the end of my presentation.
Thank you very much.
Thank you very much.
Thank you very much.